shortly. And after that, we'll be having our final exams in December.
Okay. So the semester begins in January or February?
So the semester begins in July.
Oh, in July. Okay, so you use the Northern Hemisphere timing, of course. You are in the Northern Hemisphere, after all, yes.
So
Okay.
we have a semester from July to December. And then we have another semester from January to May.
I see.
And then we have a break from May mid to July mid, I guess. Yeah. Yeah, so I believe we have a couple of participants now. So, sir, I guess we'll start. And before that, Arun, yeah, the screen is already shared. Okay, so to inaugurate this webinar on quantum computing, so the Science Forum would like to welcome you. Thanks a lot for taking out your time and showing your presence out here today. We are very grateful for you. Okay, so although the Master of Quantum Computing is present here already, still I'd like to talk about a little about this topic. Quantum computing harnesses the phenomena of quantum mechanics to solve the problems. And as we know, some calculations which might be needed for the effective simulation of real-life scenarios are simply beyond the capability of classical computers. But quantum computers have huge computational power and they can solve these problems. In fact, the development of a viable quantum computer grants such an exponential growth in computing power that it's capable of forcing a revolution in a wide range of industries. And with the luster of this topic being expressed, we will further continue talking about its distinction holder. Samiksha, over to you.
So good evening, sir. Good evening to all of you. So following this will be a few words on our admirable speaker, and they're surely going to be eye-opening for most of us. As most of the attendees already know, David is a professor of physics at the University of Melbourne, one of the world's greatest public research universities. So, founded in 1853, the University of Melbourne is Australia's second oldest university, and it's widely known for its education and research excellence. And here, he even served as the head of the School of Physics for straight 5 years. And as a matter of fact, he achieved his PhD in physics also at the University of Melbourne in 1985. So seems like it's his other home. Further, he gained experience at Caltech, USA, and he was also a postdoctoral research fellow at the most prestigious University of Oxford, United Kingdom. And I can just go never-endingly with many more such reputable credentials. And about his domain, Professor David possesses a plethora of knowledge in physics, the science of phenomena, and he has even served as president of the Australian Institute of Physics. So that's a huge list of achievements. Now, focusing on his studies and scholarly works, he has a research expertise in the field of quantum computation and communication technology. And in quantum computing and various other similar fields, he has completed a sum of 29 projects overall, which is quite huge. And for the record, he has published over 280 papers on his research work with Australian as well as international collaborators. And apparently, as we can see, he can even be awarded for his mentorship, as he has a long track record of presenting public lectures on physics-related fundamental issues. And that's why we have gathered here today.
Thank you.
Okay, so over to you, sir.
Okay, so I can now share my screen. Can you see my screen now?
Yes, sir.
Okay. Well, folks, good evening or good afternoon. Thank you very much for coming to my lecture. I want to tell you today a little bit about some of the work we're doing on the new field, the emerging field of quantum technology, and how it arose from an idea by Einstein at the beginning of the last century. We have our university is near the centre of Melbourne, which is on land formerly occupied by the Wurundjeri people of the Kulin Nation, who were the custodians of this part of Australia for tens of thousands of years. And I'd just like to acknowledge their custodianship of the land on which the university is built and where the City of Melbourne now stands. The University of Melbourne is one of Australia's oldest universities. It's located on this nice campus on the edge of the City of Melbourne. You can see the sea in the distance. And this building here is the School of Physics, and my laboratories are in the basement of this building. In the pre-pandemic era, we had over 50,000 students at any one time on our campus. It was a very busy place, including many undergraduate and postgraduate students from India and other countries, many other countries of the world. In the kind introduction, it was mentioned that our university has a very strong research track record, and this is facilitated by the City of Melbourne's very strong coffee culture. And if you ever have a chance to visit us, we can go to a nearby coffee shop, drink coffee and discuss physics. So I want to start my talk, the scientific part, with the first quantum revolution. At the beginning of the last century, the foundations of quantum mechanics were laid out by the first generation of quantum mechanics, and building on the physics from the first quantum mechanics, a whole lot of marvellous devices were built that have revolutionised our lives. Of course, fibre optic communications, solar panels, personal computer chips, the global positioning system, supercomputers, mobile phones, lithium-ion batteries, and all sorts of marvellous medical diagnostic machines, magnetic resonance imaging, and pacemakers and other implants. And of course, this today is how we communicate when we're in our cafes. No, not really like this. We shouldn't be doing this. But this shows how connected we all are because of the products of the first quantum revolution that changed the way we live our lives in the 20th century. But this revolution, although as revolutionary as it was incomplete. And we're now ready for the next revolution. So what motivates the next revolution? Well, I like very much this quotation from Paul Dirac in 1928, one of the pioneers of quantum mechanics. In 1928, Dirac said, "The underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known. And the difficulty is only that the exact application of these laws leads to equations much more complicated to be soluble." What he meant was that classical techniques of computation are not going to be able to model the real world because those classical techniques are just not powerful enough. The real world is too complicated. Now, the beginning of this second revolution basically begins with the ideas of Einstein in 1905, the miraculous year of physics, where Einstein founded 3 completely new fields of physics. But I want to focus on the one from his paper of March 17 in 1905, the idea of the light quantum, when Einstein was just a very young man. Here's the basic idea. When a beam of light approaches the surface of a metal, you can imagine it as a series of waves approaching the surface of the metal. But Einstein realised from the experimental data that this beam of light is not distributed continuously over the surface of the metal, but consists of a finite number of small quanta, energy quanta, that are localised at points in space and move without dividing and can be absorbed or generated only as a whole. So here is the light quantum that accompanies in some way this wave. And the picture that Einstein was presenting to us was that this is how the quantum of light approaches the surface, it somehow is everywhere at once, like a wave over that surface. But when it hits the surface, it is all absorbed just by one electron. This is sometimes called the wave-particle duality. The wave is spread out over all space, but the particle is highly localized. So this brings us to the idea from this revolutionary idea for which Einstein later won the Nobel Prize, is that a quantum particle, like a photon of light, can be in many places at the same time until it is measured by this electron in my example here, where the whole particle collapses just to that single point and transfers all its energy just to one electron. And although Einstein outlined this theory for photons, for light waves, we now know this works for particles like electrons and other quantum mechanical particles as well, matter as well as photons. Now let's move to 1959, when Richard Feynman, who I met when I was a postdoc at Caltech, he's long since passed away now, a very engaging scientist, he put forward this revolutionary idea that in the future of 1959, we could use computers made of circuits involving quantized energy levels or the interaction of quantized spins. He gave this marvelous lecture. I invite you to look it up. There's plenty of room at the bottom, where he outlined the new physics that is possible when we harness the fundamental quantum building blocks of nature. So this is what Einstein was thinking about. In my example here, I've got a phosphorus atom, which has a nucleus with a spin 1/2, and the last electron added into the valence band, this phosphorus atom, also has a spin of 1/2. And these are the spins that we could harness for a new type of computer, a quantum computer. So here's the basic idea. All classical computers, since time immemorial, follow the same principles as this classical abacus. Here we have a series of bits that can be up or down on a wire. When the bit is down, we call it a 0. And if you flip the bit through 180 degrees, it goes up, and we now call that a 1. And a classical bit can only be up or down, 0 or 1. Nowhere in between makes sense. But now imagine you took the wire of this abacus and you broke it out of the frame and allowed it to have any orientation in space. This now is the illustration of the power of a quantum bit, because a quantum mechanical spin can be oriented at any point on what is called the Bloch sphere. It's like a bead on an abacus where the wire can occupy any orientation in space, not just up and down like a classical abacus. And so now you can encode an enormous amount of information depending about where on the Bloch sphere the spin is oriented. And we write this mathematically as the superposition of the two classical values of up or down. And when you measure this quantum spin, you find, of course, that it only has two possible values, 0 or 1, just like the classical spin. But with the measurement, you can harness this quantum mechanical attribute to do computations, enormously powerful computations because of the ability of the spin vector to point to any Bloch sphere. So fast forward now to 1998, where this remarkable paper appeared by Bruce Kane, South Wales, up in Sydney, called a silicon-based nuclear spin quantum computer. Bruce's amazing idea was to insert phosphorus atoms into a block of silicon, put them very, very close together, only 20 nanometers apart, and control them with electrodes so that the quantum states of either the electron spin or the nuclear spin could be programmed, coupled, and read out. A truly revolutionary idea. And this paper today has had over 3,000 citations and triggered a revolution in the ideas of computation. And we're very grateful to Bruce for having this revolutionary idea that has been so very productive. So today, we now realise that building the Bruce Kane quantum computer would be very difficult. But all sorts of new architectures have evolved by this one, by my colleagues. This is one by Professor Andrea Morello from the University of New South Wales, which he calls the flip-flop qubit, where we have two phosphorus atoms inside a block of silicon, coupled to electrodes on the surface, which can be used to control the two phosphorus atoms. And by biasing the phosphorus atoms and distorting the electron clouds, you can generate an electric field that couples the two phosphorus atoms together and can put them in a quantum mechanical superposition. So this is a bit in a large-scale quantum computer, which is on a more relaxed scale than the very small scale needed by the Kane computer, that we can build with more or less conventional technology. Now, the idea of using quantum spins for computation and the fact that they can be put into a superimposed state of 0 plus 1 is just one of a whole lot of different quantum mechanical attributes that could be harnessed for new technologies. So there's quantum entanglement as well, called by Einstein spooky action at a distance. Basically, the idea here is you could have two photons which are coupled together, despite the fact they don't exchange information between them, but their polarization states are complementary always. If you measure one to be horizontal, the other one will become vertical, even though there is no communication between them. This is an inexplicable quantum mechanical attribute that has no classical explanation. Of course, quantum mechanical particles can tunnel through potential barriers, and this phenomenon is already harnessed in Esaki diodes that won the Nobel Prize back in the 70s. And of course, thermonuclear fusion in the sun burns by quantum mechanical tunneling of protons through the Coulomb barrier. And it has other applications as well. Quantum mechanical coherence is the attribute of superimposing spin states, as I've explained for computation, but these are coherent electromagnetic mechanisms that happen inside living cells. And of course, there's the phenomenon of teleportation, where quantum states can be transmitted over long distances, which leads to secure communications, where security is guaranteed by the laws of physics rather than human ingenuity. So we'd like to exploit these new technologies, of course, as quantum computing. We'd like to be able to address Dirac's problem that even though we know the Schrödinger equation in great detail, we cannot use it even to solve the structure of a caffeine molecule, because there are 100 electrons in this molecule and it's impossible for a classical computer to model the structure. The best classical computer today could only do about 30 electrons. So this is many orders of magnitude too complex for even the best classical computer. And who knows, in the future, vaccines for new viruses could be designed inside a quantum computer rather than the traditional methods of using test tubes and clinical trials. I mentioned quantum sensing. Nitrogen vacancy color centers in diamond have very nice superimposed states even at room temperature and can be used inside the body. Cryptography for secure communication, and one day, perhaps in the middle of this century, there'll be the quantum internet, which couples vast networks of quantum computers together to do enormous computations impossible today. So this will lead to the second quantum revolution, harnessing directly the quantum attributes that underlie the first quantum revolution. And all around the world, in the United States, China, the European Union, my own group here in Australia, which is a consortium of laboratories on the east coast of Australia, in the United Kingdom, and of course in India, there are now major programs aimed at harnessing the benefits of the second quantum revolution. So let me just say a few words about the work we're doing at the University of Melbourne. My laboratory has a large particle accelerator that provides beams of ions that we use for analysing silicon crystals and measuring the internal electrostatic landscape of the devices we're using for the quantum computer project using high-energy ion bombardment. And we also have clean rooms in the basement where we can make devices, and a low-temperature measurement system where we can cool devices down to 10 millikelvin in a 9 Tesla magnetic field. We have a small ion implanter which we can use for putting one atom at a time inside blocks of silicon, and we have a device for measuring the quantum state of our implanted atoms in silicon devices. So the basic physics we're trying to harness comes just from first-year physics. I'm sorry, I didn't realise my audience would be very well educated, and I don't want to insult your intelligence, but I just wanted to remind you of some first-year physics. If you put two magnets together so that the poles are in opposite direction, they'll stick together. This is the low energy state of these two magnets. But if you flip one of them around so the like poles are together, that will spontaneously decay to the low energy state when one of the magnets flips. So this is a two-state system, a low energy state, a ground state, and a high energy state. Likewise, when you put our phosphorus atom into a magnetic field, the nucleus spin and the electron spins can be flipped into a high energy state when they're in a strong magnetic field because of space quantization. Both the nucleus spin and the electron spin are spin half, and so they have two possible energy levels, just like they are little magnets based on the magnetic moment of the quantum spin of either the electron or the phosphorus nucleus. Either of these can be used as qubits. And of course, if you look at light coming from the sun, you can see light coming from sunspots when you pass it through a prism splits into discrete lines because of the spin state of the atoms that are being heated up inside the huge magnetic fields in the sunspots of the sun. Now, this is what we're trying to do. Here's a block of silicon at the seen at the atomic level. Natural silicon consists of three isotopes. Silicon-28, the abundant one, 0 nucleus spin. The problematic silicon-29 with a spin half nucleus, about 5%, and the rest is silicon-30, again with 0 nucleus spin. And so here we can replace one of those silicon atoms with a phosphorus atom in a silicon chip where we can program the spin of the phosphorus nucleus or the associated donor electron. But the problem is, in natural silicon, there are all these silicon-29s which act like little uncontrolled bar magnets that decohere the delicate quantum states we want to program into our qubit. So we have developed a technique in Melbourne where we can get rid of those silicon-29s and replace them with silicon-28s. And this becomes enriched silicon-28, otherwise known as the semiconductor vacuum. No background spin, the next best thing to a real vacuum for doing quantum mechanics. Now, here we've got a 0, a nucleus spin up, or if we program the electron spin is down. Now we can flip the spin so that the nucleus spin is down or the electron spin is up. Either of those represents a 1 qubit. Now, by bombarding this with photons, we can put the spins into the up state and the down state simultaneously to make a qubit in a superimposed state. And as long as we don't measure it, and as long as we don't have any stray silicon-29 atoms left in the crystal lattice, these superimposed states of up plus down last for a very long time. This is how the device works. We've got, we're down inside the block of silicon, which is invisible, looking up towards the surface. Here are electrodes. Here is a phosphorus nucleus. And this electrode on the surface is controlling the phosphorus nucleus. We put an electron on the nucleus. Then we apply a pulse of microwaves, which can flip the electron spin. And then we can read out the electron spin by moving it onto a nearby single electron transistor where a current of electricity flows through the device, which can be measured in an external circuit. and then we can put the electron back again. So this is a qubit under full control using electrodes on the surface of a block of silicon. It's very small. And this is how we put the electron spin into the superimposed state. Here's the spin up and the spin down states, and here are the photons coming in, which flip the spin from the low energy state to the high energy state. But the same photon will also induce the spin to flip from the high energy state to return to the low energy state. So as long as those photons are on, the spin is in the superposition up plus down. This is the spooky quantum attribute where it's in two states at the same time. Sorry about that, I'll get rid of that. And so now we can measure the electron spin orientation with our device, and it can be down or it can be up, and we can repeat that measurement as often as we like. Now, classically speaking, you would expect that 50% of the time when you measure the spin, it would be up, and 50% it would be down. And of course, Galileo and Newton would say, yes, that's what you would expect to see if this was, because they only knew about classical particles. But when we do the experiment, and here's the device we use to do the experiment, this is a scale bar of 100 nanometers. This is about 10 million times actual size if you're looking at it projected on the wall of a lecture theatre. Here is a place where we implant our phosphorus atoms. Oh, I should have mentioned we get rid of the silicon 29s first. Then we implant some phosphorus atoms. And then by controlling the electrodes, we can tune into just one phosphorus atom and program it with a microwave pulse down this antenna integrated into the surface of the silicon. And we find that the superimposed state on an electron will last for a quarter of a second, which is an eternity for a superimposed quantum state. And the nucleus will last for more than 30 seconds. That is effectively forever. You could do billions of computations in 30 seconds of coherence time. This is a very robust quantum system. And this was one of our first measurements of one of these devices. This shows highly non-classical behaviour, because when we measure the spin up probability, so the probability of being in this state, as a function of time after the microwave pulse, we see that it oscillates up and down between the 0 probability, so it's in the down state, to 1 probability, meaning in its up state. These are Rabi oscillations, which are characteristic of a quantum system. And so, of course, to observe these, you need to have an observer. And so here we are in the lab watching our single nuclear qubit and our single electron qubit flipping up and down a few years ago. It was a very exciting time for our experiments. So we've used this system to demonstrate a lot of single donor physics. We've done a Bell's inequality violation to show that there are no hidden variables in superimposed quantum states. We've measured these long-lived single nucleus spin coherence times, and we've even built devices in which we've got two atoms that we coupled together with a single electron. And above all, we've developed techniques for building a large-scale device. So just to conclude, let me explain how we want to build this large-scale device with hundreds of qubits. The basic idea is shown here. We take our ion beam in an atomic force microscope with a cantilever that's got a very tiny aperture into it, drilled into it. And we allow the cantilever to hover over the substrate until one ion passes through the tiny aperture and embeds itself into the substrate. This is the technique of ion implantation. And we have electrodes on our substrate which are connected to a sensitive preamplifier. And this is what we hear as we irradiate our sample. I hope you can hear that. That's very noisy because there's a lot of background noise, but those pings are the sound of single atoms passing through the cantilever and embedding themselves in the substrate. And by moving the cantilever after each ping, we can build a large-scale array of single atoms implanted in the silicon substrate. And this is the machine we built to do this. And this is the large-scale device we're planning to make over the next few months using this technique. Oops, sorry. So there are still many challenges ahead for us in this field. But we're now entering what's called the noisy intermediate scale quantum technology era. Some of the largest quantum computers available today from IBM and Google and other companies have more than 50 qubits, which can be programmed. But our aim is to go way beyond 50 qubits. We would like to build a fault-tolerant quantum computer with over 1 million qubits. Atoms, ladies and gentlemen, are really cheap. To build a 2-qubit device or 1 million qubits, it needs only a tiny number of atoms. Of course, a lot of circuitry and a lot of electronics, but it's a very compact qubit. And we believe the future lies in atomic qubits. So thank you very much for your attention. I'm very pleased to answer any questions you may have on this very brief introduction to this new field.
Thank you so much, sir. This was something that at least I wasn't aware of being a chemistry student. This has been very interesting. Now, those who want to ask questions can simply raise their hands and we'll unmute them after that. And by the time I can ask some of the questions that I had received earlier.
So I see there are some questions there.
So Arun, could you please unmute them one by one?
Yes, sir. Sir, am I audible?
Yes. Good afternoon.
Good afternoon, sir. Sir, I wanted to ask a simple question. In the beginning slide, you said about bits and qubits. Sir, there I have a doubt that having a qubit, how can it make a quantum computer powerful?
So the qubit stores effectively a large amount of information per qubit, because the qubit can be in 2 places at the same time. So instead of just having a 0 or 1, each qubit has 0 and 1. And so if you have a very large number of qubits that are coupled together, you can store in your n qubits 2 to the n pieces of information effectively simultaneously. This is not strictly true, but this gives you an idea of the massive parallelism possible by using qubits instead of classical bits. In a classical memory, you can only store 1 piece of information at a time, because each bit has to be either 0 or 1. But so if you've got n classical bits, that's only 1 number with n digits. But in a quantum computer, you have 2 to the n pieces of information because of the superposition effect of being 0 and 1. It's like to give you a semi-classical example of what I mean. Imagine you're doing a Young's 2-slit interference experiment. Okay, so you've got a barrier which has got 2 slits in it. And you don't know that it's got 2 slits, but you've got a whole lot of classical particles which you can throw at the barrier and then look at the shadow of the barrier cast by all those classical particles hitting the barrier. Most of them will hit the barrier and bounce away, but a few will pass through the slots and make a shadow on a screen. And you can look at the shadow and say, oh yeah, I see 2 lines, there must have been two slits. But if you do that experiment with quantum particles, like photons, when the photon approaches the screen, each individual photon goes through both slits. I'll say that again. A photon is a quantum particle, so it can be in 2 places at the same time, and each photon goes through both slits and makes an interference pattern, not a classical shadow anymore, but an interference pattern. And when you take the Fourier transform of the interference pattern, you can reconstruct the fact there must have been two slits that these quantum particles pass through. But if you were doing this experiment and there was another slit in the barrier or another hole somewhere in the barrier, you'd have to throw millions and millions of classical particles to find that extra slit or that extra hole so that it made a shadow on the screen. But you can be confident that if you use quantum particles, every quantum particle will go through every slit, every hole, every pathway to get to the screen and participate in making an interference pattern. And so that's a very powerful way of solving the problem, answering the question, how many apertures are there in the barrier? Use quantum particles. Every quantum particle probes every square micron of that barrier to give you the right answer. But the classical particles don't. They only probe 1 square micron at a time, and you've got to use lots of them. So that's what I like to think of as the power of quantum computing compared to classical computing. You basically probe the entire phase space simultaneously rather than doing it pixel by pixel as you'd have to do with a classical computer.
So I hope that solves your query, Sarkar. Next.
Yes. Who's next?
Hello, sir. Am I audible?
Yes, I can hear you.
Sir, good afternoon. Sir, my question is how NV centers can be used as qubits?
I beg your pardon?
Sir, how NV centers can be used as qubits?
Yes, a very good question. In Melbourne, we also have a big activity on NV centres in Diamond. But in 25 minutes, I didn't have enough time to say very much about it. So the wonderful thing, first of all, the wonderful thing about Diamond is that it has a very wide band gap and is a very rigid crystal lattice. So for Diamond at room temperature, it's like silicon at 10 millikelvin. So there's very few lattice vibrations that can degrade the coherence time of your qubits. Now, the nitrogen vacancy color center is where one carbon atom in the diamond crystal has been replaced with a nitrogen atom, and next to the nitrogen atom, there's a missing carbon atom. Because the diamond lattice, as you probably know, is very, very dense. The carbon-carbon bond is very, very strong. That's why diamond is so hard. And so there's no room to put foreign atoms. Not like silicon. You can put phosphorus, you can put antimony, you can put arsenic, you can put bismuth, no problem. But in diamond, it's very difficult to get another atom into the crystal lattice. There's no room. So you have a nitrogen atom, and you need a vacancy in the crystal lattice to make room for it. Now, it turns out that the quantum state of this defect in the diamond crystal lattice, it's got about 8 electrons in orbit around the nitrogen vacancy color center, has 2 energy levels, a ground state and an excited state. It's a collective excitation of the electrons orbiting the color center. And you can read out the quantum state of this defect optically by bombarding it with photons. And if you like, depending on the colour of the photon you get back, you could tell whether it was in a 0 ground state or a 1 excited state. And just like with the phosphorus atom in the silicon lattice, you can bombard it with microwaves and put this collective excitation in a superimposed state of the ground state plus the excited state. And the coherence time is very long, even at room temperature. So for a diamond quantum computer, you don't need to cool it down to 10 millikelvin. The problem is that it's very difficult to engineer devices in diamond. Of course, silicon is a fantastic material for making devices. You can make 100 billion transistors in a Pentium chip and buy it for a few $100s. That's amazing. And at the moment, the diamond community is doing lots of experiments with single qubits, which you can make one at a time in the diamond crystal lattice, but not on demand, really, not yet, though there's some people trying to solve this problem. And there are people working on trying to make a large-scale device with hundreds or thousands of nitrogen vacancy centres all coupled together and controlled by electrodes. And if that engineering problem is solved, we need some good PhD students to come and work on this problem, this could be really, truly revolutionary, and we might have quantum Pentium computers built from diamond that operate in our mobile phones, for example.
Thank you, sir. So there is a follow-up question that like nitrogen vacancy center, HBN has also defects, hexagonal boron nitride. So can it be used as a qubit?
Sorry, which color center?
Say, hexagonal boron nitride.
Oh, yes.
It has several defects.
Yes, yes, indeed. But that's a good point. Many crystals have color centers or defects that emit light. But the problem is you need a crystal with an extremely clean band gap. So in a semiconductor crystal, you have electrons at 0 Kelvin anyway that fill up to the top of the valence band. And then you have a forbidden gap because of quantum mechanics, and the next available levels are in the conduction band. And the silicon and diamond you have extra energy levels inside the band gap because of engineering. In the case of silicon, you engineer phosphorus or boron if you want p-type. And in diamond, you engineer the nitrogen vacancy center. But many other materials like boron nitride are very difficult to make with a clean band gap, because you don't want a band gap with lots of little levels from dangling bonds or foreign atoms or crystal defects, because all of those will decohere your qubits. So if you can make a large wafer or a large crystal of boron nitride and then engineer single color centers without introducing extra defects, that would be a very interesting system. But at the moment, I don't know of any color centers that are decoupled from other defects in boron nitride that would be good qubits. I'm not saying they don't exist, but I don't know that anyone's found one yet. If they do, that could be, and they figure out a way of growing very perfect single crystals of boron nitride so there are no defects in the band gap, that could be an important innovation.
Thank you, sir.
Good afternoon, sir.
Good afternoon.
Sir, we are in very early days of quantum computing, and like in classical computing, we have transistor as a standard used for storing bits. But in early days, we use various techniques like vacuum tubes and mechanical switches. So here we have many technologies for qubits like NV centers, photon polarization, electron spin, nuclear spin. But some are scalable, some are dependent on the temperature. So which technology do you think will win the race of being a standard qubit for future scalable quantum computing?
Well, that's a very good question. And you're asking me? Phosphorus in silicon is the answer, because we already know how to build millions or billions of devices in silicon. It's a remarkably friendly material for engineering large-scale devices that are very compact and very small. So you could imagine that a 1 million qubit device will need 100 million transistors to control the coupling between the qubits, to program them and read them out. So you'll need a layer of CMOS circuitry to control your phosphorus spin qubits in an isotopically pure silicon matrix. There are not many other materials that can be scaled in the same way. The photonic qubits need very complex infrastructure. Ion qubits now are starting to look like silicon chips, but the chip is the control circuitry for generating the electric fields for controlling suspended ions in a vacuum that are programmed with lasers. But these tend to be big, in my view. So I think if we really want to be able to design new drugs or solve the molecular structure of organic molecules, we're going to need millions or even billions of qubits, especially if we want to encode information in a way that's robust against decoherence. Because as I explained, the environment can interact with your qubit and destroy the quantum superposition, in which case the calculation fails. And so there are a lot of people working on error correction techniques, so that if a stray photon or a stray lattice vibration destroys the coherence, the calculation doesn't fail. And one way of protecting against decoherence is to encode a logical qubit on 5 physical qubits. So if one physical qubit suddenly loses its superimposed state and decoheres to the classical state, you can recover the quantum information from the other qubits. So one logical qubit in a large-scale processor might consist of 5 physical qubits so that you can guard against decoherence. That's a very important field investigation. And I should point out that this is my 128 gigabyte memory stick that I use for backing up my lectures. 128 gigabytes, look at that. That's amazing, amazing technology. But many of those bits don't work, because this is really pushing the technology, CMOS technology. So this memory stick has an EEPROM that monitors the health of all the bits in this memory stick and closes off bits that don't work properly. So gradually the number of bits that are available for storing information will decline. So this is an example of a fault-tolerant classical device where the engineering is not perfect. Some bits don't work, but the control circuitry is able to work with that and continuously monitor the health of the memory bits and close off the ones that don't work properly so that you don't corrupt your data. So industry, in making these large-scale devices, is already has lots of techniques for guarding against defects. And I think a large-scale quantum computer will be the same. We might have 1 billion qubits, of which a few million don't work, but the architecture will be sufficiently robust, like this, to bypass the ones that don't work and don't use them for the computation. That's my view. That's still a long way off. There's some very difficult engineering problems to solve, but we're already used to doing that with classical devices anyway.
Who's next?
Hello, Professor.
Hello.
I would like you to please explain once again how do you replace that silicon 29 with silicon 28 in order to solve that problem, because I lost your voice at that point.
Right. Actually, I didn't explain how we did it. I just say we have a method that we use to do it. Yes. Our method involves high fluence ion implantation. So in a standard industrial ion implanter used for making, well, memory sticks, Pentium chips, there are about 15 different ion implantation steps. needed to put the dopants into the silicon crystal to configure the devices. Now, it turns out that an industrial implanter can also implant isotopically pure silicon-28. And if you implant at exactly the right energy, what happens is a silicon atom comes in, a silicon-28 atom comes in, and one atom from the substrate is dislodged into the vacuum. So over time, when you irradiate with only silicon-28, you deplete the silicon-29 in your substrate. And this is our method for making isotopically pure silicon-28, using the same tools that we use for implanting the qubits. We have a paper on this technique that was published last year.
Okay, thank you.
But you can also buy silicon-28 wafers commercially, but they're very expensive. And also, you might have seen in the news that the standard kilogram, which used to be a kilogram of a platinum iridium alloy kept in a argon environment in a bank vault in Paris, has now been made obsolete. It's been replaced with a standard kilogram made of isotopically pure silicon-28, which can be made very pure and very precisely, and that is now the standard for the kilogram, not the platinum iridium cylinder anymore. And we managed to get hold of some fragments of the silicon-28 that was left over from making the new standard.
No, thank you, sir. Okay.
Hello, sir.
Hello.
So after phosphorus ions have been implanted into the crystal, you used microwaves to basically generate the superposition. So do you exactly know the superposition state, like the constants A and B, based on the say frequency or some characteristics of the microwave radiation used?
Yes, you can choose the A and B depending on how you irradiate the qubits. So for putting the electron spins in the superposition, indeed you use microwaves, because that's a microwave photon has the right energy to flip from the low energy state to the high energy state and vice versa. And for flipping the nuclear spin, you use radio frequency because the nuclear spins are much smaller and you don't need nearly as much energy. So yeah, it's
and do we also know the rate, like the Rabi oscillations that you mentioned? So that also can be tweaked in some sense?
Yes, indeed. Yes, it can.
Okay, so that is the basis of the whole the structure. Like
yes.
The superposition structure that you construct.
Yes. Those Rabi oscillations are a signature of the quantum superposition. And by the way, before we managed to make a device in isotopically pure silicon-28, we just used natural silicon. And we saw those Rabi oscillations, but we only saw about 2 of them or 3 of them before they decayed to 50% if we were measuring the spin-up probability. So in other words, the background silicon-29s in our natural silicon device decohered our qubit, so we only saw a couple of those Rabi oscillations. I should have shown you the first result in natural silicon, because you'd be amazed to see that when we moved to silicon-28 and got rid of the silicon-29s, the Rabi oscillations went on forever. It was just amazing, the difference. It was a wonderful thing to see. I mean, I've been teaching quantum mechanics to first years for 2.5 decades, Zeeman effect, superposition, all of that. And then to go into the laboratory and see with my own eyes a single nuclear spin flip from up to down right before my eyes was a wonderful experience in a device that we had made. I can't tell you how wonderful that experience was. So it wasn't theory anymore. It was real there in the laboratory on the oscilloscope screen.
Indeed, sir. Yeah, that sounds really wonderful. Okay, sir. Thank you. Hello.
Yes, hello.
Yeah, sir. My doubt is that we are using electron spin for building quantum computer, right? Can we use proton spin also?
Yes, that's a very good question. And in fact, in the early days, back in the late 1990s and early 2000s, an ensemble quantum computer was demonstrated at the IBM laboratories in the United States. So what basically they did was took a molecule that had carbon-12 and carbon-13 and protons, a hydrocarbon, obviously, but some of the carbon-12s have been replaced with the spin-half carbon-13 nucleus. And then using NMR, nuclear magnetic resonance, they were able to program quantum states, but not onto just one atom at a time. It was an ensemble of atoms in this liquid. So the qubits were distributed over the entire volume, over many, many molecules, using NMR as you ask, and that was a pioneering demonstration that the ideas were sound. This was not a very useful quantum computer because you couldn't control the coupling between the qubits, because the coupling was determined by the position of the spins in the molecule, and you didn't have any electrodes where you could turn the coupling on and off. But it was one of the first demonstrations of a quantum algorithm on ensembles of qubits in a liquid in solution using NMR. I think it was 6 qubits they had.
I also have one more question, sir. I am a student of physics basically, and I want to pursue my education in a quantum information. So, which reference books or paper would you like to refer us?
Oh, right. Okay. Well, there are very many, and new books are appearing all the time. One of my colleagues in the United States has published a popular book called Quantum Computing: A Gentle Introduction. She calls it a gentle introduction, but it's very deep. So that's a good place to start. But there are many possible other books as well. But that's one that immediately springs to mind.
Okay, sir. Thank you.
Good afternoon, sir. Am I audible?
Good afternoon. Yes, you are.
So first of all, thank you. I think that was a very interesting talk. My question is similar to what Abhinav asked. I just wanted to know about how the various quantum logic gates would actually be implemented in this architecture. I understood that the superposition would be carried out with the help of microwaves, which would control the coefficients. But how the more complicated like C0 gates and things like that would be carried out in this architecture?
Well, yeah, okay. So in our devices, if we can do a C0 gate between the electron spin and the nucleus spin by controlling the overlap between the electron and the nucleus. That's like a 2-qubit device right there, but it's not. It's just a physics experiment because we don't have very much control over the 2 qubits because the electron is orbiting the nucleus. But in the case of the flip-flop qubit, you can. We haven't done this experiment yet because it's very well. We've done the experiment on 2 phosphorus atoms, which we implanted that happened to be very close together. We didn't engineer the spacing, we did a random implant, and we happened to find a device where there were two atoms that were close together. So by controlling by putting an electric field gradient across the place where the two atoms were located, you could tilt the electrostatic potential and bring the electron from one atom to the other atom, depending on which way you put the electric field. And with that device, it was possible to demonstrate a C0 gate. But that was, again, in a device. We were very lucky that there happened to be two phosphorus atoms close enough together that we could couple with the potentials that we had available from the electrodes without blowing up the device. But we now, with our single atom implanter, now that we've got that working, we're hoping to build a much better device where we actually control the position of each phosphorus atom and try and make a two-atom device or even more in the near future. So a proper engineered 2-qubit device, not one that was just made by luck. But it's all programmed by the bias voltages applied to tilt the electrostatic landscape and couple the qubits together.
Thank you, sir.
Thank you, sir. Thank you for answering all of the... Hello, am I audible? Okay. Thank you, sir. Thank you for answering all of the questions and taking out the time for it. And it was an extremely knowledgeable lecture. Just to comment on the choice of the topic, I'm sure that all our aspiring researchers would have taken notes, and it was a healthy interaction. It's fun to extend our knowledge out of the course books, and this became possible because of your lecture. And that's why the Science Forum would like to express its gratitude to you. We're really looking forward to a profound mentor and student's relationship with you. Thank you.
Well, thank you for providing such an excellent audience. It was a great pleasure. And best wishes for your future studies and future careers. I'm sure you'll do well. Thank you.
Thank you so much, sir. It was just a 1 minute from our side, and it was a big yes from yours. So thank you so much for accepting our request.
Okay.
Thank you.
Okay.
Thank you.
Good night. Good afternoon.
Good night to you, sir.
And I'm also grateful to the audience for being patient, interactive, and for sticking to the event and making it a great success. Thank you for all the interaction as well. All of you have a really nice day. And we would love if you would reply on our feedback forms, and we're going to send them in the WhatsApp groups designed for the webinar. We would really love to have some honest replies. Thank you, all of you, and have a nice day.
Thank you.